Hello everyone, my name is Tanmoy Das. I am a lecturer in chemistry at Kalichok Government Polytechnic. So in today's topic, we are going to know about stereochemistry. Stereochemistry is the branch of science which deals with the structures in three dimensions. And there are several applications of stereochemistry including biological systems, development of therapeutic agents or drugs, and even tasting a compound or smelling a compound also involve the branch of stereochemistry. Now, one important aspect of stereochemistry is stereoisomerism. To understand stereoisomerism, first of all, we need to understand what is isomer. So, isomers are chemical compounds having same molecular formula, but they are somehow different. So, isomers can be categorized into two classes. One is constitutional isomers, where molecules having same molecular formula possess different functional groups. But in case of stereoisomers, the arrangement of atoms inside a molecule is different as compared to the other isomer. And stereoisomers can be classified into cis-trans isomers as depicted here. Here you can see that in case of cis-2-pentene, both methyl as well as ethyl groups are present on the same side of the double bond. But in case of trans-2-pentene, methyl and ethyl groups are present on the opposite side of the double bond. Now coming to the second part of stereoisomerism, which involves chiral centers. Before moving into details, we need to know the topic chirality. And chirality is always associated with chiral objects. So a chiral object has a non-superimposable mirror image. And the best example of a chiral object is our hand. Our right hand is not superimposable to our left hand. But on the other hand, achiral objects like chair, these types of objects can be easily superimposed over the mirror image. So here I have shown an example of chiral object. This is the structure of lactic acid. But if you closely monitor the structures of these two molecules, both are lactic acids, but one cannot be superimposed over the other one. And that's why lactic acid is a chiral object. But if you closely monitor the structures of the lactic acid, you can easily see that the structure of the lactic acid present on the left side is the mirror image of the lactic acid present on the right side. And these kinds of arrangements are called enantiomers. Just like the case of lactic acid, you can also visualize the case of butane. Here also you can see that the butane present on the left side is the mirror image of the butane present on the right side. So can we call them enantiomers? No, because there is a CC single bond, and via rotating the CC single bond we can convert the left sided butane into the right sided butane, and these kinds of arrangements are called conformation. Now, one important problem while handling the enantiomers is their same physicochemical properties. So how can we differentiate different enantiomers? First one is the interaction of plane polarized light with enantiomers. Ordinary light is unpolarized light, but if we pass the ordinary light through a Polaroid filter, light only oscillates in the one direction, and that is called plane polarized light. And these enantiomers, for example the left-handed enantiomers, interacts with the plane polarized light in such a way that it rotates the plane of polarization in the anti-clockwise direction. But on the other hand, the enantiomers present on the right hand side will interact with the plane polarized light in somewhat different manner, and via the interaction process the plane of vibration of the plane polarized light will rotate in the clockwise direction. There is another method via which we can differentiate these enantiomers, and that is the interaction with other chiral systems. So levorotatory and dextrorotatory enantiomers interact with a chiral reagent differently. For example, if the levorotatory enantiomer interacts with a chiral agent strongly, then the other enantiomer will have loose interaction. So at this juncture, we came to know the differentiation process of enantiomers, but they are having same functional groups attached at the same carbon. So their IUPAC nomenclature will be same. So what is the way to differentiate these enantiomers via nomenclature? So there is one rule, that is Kahn-Ingold-Prelog rules, where we can assign R or S notation to a particular enantiomer. Utilizing these rules, we can easily assign R or S nomenclature to a particular enantiomer. For that purpose, we have to rank those functional groups attached at the carbon center. So the higher molecular weight functional groups will be uh, termed rank 1, followed by the ranking will be provided on the descending order of molecular weight. Now we have to project our views in such a way that the lower or lowest priority functional group stays as much away as possible from our eye, and in this way we have to move our arrow from 1 to 2 to 3. If it is going in the clockwise direction, the notation will be called R, and on the other hand, if the rotation is going in the anti-clockwise direction, then the nomenclature will be called S. But there are several other examples where chiral systems can be generated in absence of chiral centers, and the examples are allene or helicine or biphenyl systems, etc. So in this small presentation, now coming to the conclusion part, the importance of stereochemistry has been described in this lecture, and the basics and several aspects of stereochemistry has also been highlighted. Thank you very much for your attention.